General orthogonal expansions, a survey of the orthogonal expansions we've studied so far this semester. In chapters 2 and 3, we studied Fourier series techniques, namely the infinite series expansions of functions in terms of the cosine and sine functions. The study was based totally on the eigenvalue equation S double prime plus lambda S equals 0. The table below from the inside front cover of your textbook shows the eigenvalues and eigenfunctions of the 5 types of boundary conditions we've studied combined with this differential equation. The first row gives the eigenvalues and eigenfunctions for the boundary conditions Dirichlet. The second row is for Dirichlet-Neumann boundary conditions, the third row Neumann-Dirichlet, and the fourth row Neumann-Neumann. And finally, the last row is for a periodic boundary value problem. In chapter 4, we studied Sturm-Liouville theory, which generalized the basic eigenvalue equation to the Sturm-Liouville form shown here. We found that the orthogonal expansions of functions in terms of sines and cosines were in fact simply special cases of this more general theory, as illustrated in the following table comparing the Fourier series of a function with the general weighted orthogonal expansion. The first 3 rows in this table describe the expansion and formula for the coefficients for the Fourier sine, cosine, and full Fourier series. Finally, the 4th row is the general weighted orthogonal expansion of a function in terms of a general set of eigenfunctions, x sub n, a complete orthogonal family, and on the right we have the familiar formula for the coefficients. The essential feature for us was the space L2W, the vector space of weighted square integrable functions on the interval AB. Here's the table from the definition, from page 96 in your textbook. We call the space L2WAB, it's the space of real valued functions whose weighted square integration, weighted by the weight function w of x, is finite. It's based on the weighted inner product given here in the definition, and we call it the space of weighted L2 functions on the interval AB. The weighted inner product naturally defines the weighted norm that we also refer to, and we call this the weighted L2 norm on the interval AB. We found that the general solution of PDEs in terms of infinite series built up from eigenfunctions. We suppose that we have a basis, that is a complete orthogonal family, xn, n from 1 to infinity, of this vector space L2WAB. If f is any function in that space, and we expand it in an eigenfunction expansion in terms of our basis, with the familiar formula for our coefficients in terms of the weighted inner product, then the series converges to f in the L2 sense. The key then is to find bases of the vector space L2WAB, i.e. complete orthogonal families of eigenfunctions. The Sturm-Liouville theorem provides us with the tools to do this. Theorem 4.3 on page 120 tells us that the eigenfunctions of a regular Sturm-Liouville problem forms a complete orthogonal family. Theorem 4.5 on page 125 tells us that the eigenfunctions of a periodic Sturm-Liouville problem also forms a complete orthogonal family. And the discussion in the textbook, not numbered, of the Sturm-Liouville theorem for a singular case guarantees that the eigenfunctions for a singular Sturm-Liouville problem, also forms an orthogonal family. The question of whether or not the family is also complete is left to more advanced courses, but your author guarantees that the polynomials that we study, namely the polynomials of Chebyshev, Laguerre, Hermite, and Legendre, as well as the Bessel functions, are all complete as well as orthogonal in the space L2WAB. Let us survey then the table on the inside back jacket of your textbook reproduced below. This is the table you'll be able to use when you on test 2 and the final exam. It's a little difficult to read, so let's survey the Legendre column and the Bessel column. The second row gives us Legendre's equation then on the interval -1 to 1. The Sturm-Liouville equation is given in the fourth row, and the weight function for Legendre's equation is 1. The eigenvalues and eigenfunctions are displayed. Lambda n equals n times n plus 1, starting at 0. And the eigenfunctions are the Legendre polynomials of the first kind, denoted p sub n of x. The Legendre polynomials are listed in most computer algebra systems. The one shown here is for Mathematica, I believe. And if the square brackets around n and x, n comma x, were round brackets, that would be the notation for the Legendre polynomial p sub n in a Maple worksheet. The final row is the L2 norm for the Legendre polynomial p sub n. Finally, let's survey the eigenfunctions and eigenvalues that come from Bessel's equation. Bessel's equation, in the second row here, this is Bessel's equation of order n with parameter lambda. It's defined on the interval 0 to L, and the fourth row is the Sturm-Liouville form of Bessel's equation with weight function x. Next are the eigenvalues and eigenfunctions. The eigenvalues are given in terms of the zeros of the Bessel functions, z sub nm. Z sub nm is the mth zero of j sub n of x. And the eigenfunctions then are given in terms of j sub n evaluated at the z sub nm times x over L. The Bessel functions were also tabulated in most computer algebra systems, and here we have the notation from Mathematica. And again, if the square brackets were round brackets, we'd have the notation for Bessel j sub n in a Maple worksheet. The last row is the L2 norm for j sub n of x.